a really, really hot topic. So we had about a few hundred people register for the recording on this, 300-400 people, and it's good to have 30 people here actually just listening in. So really what I want to do is look at a few issues with catastrophic failure, and then look at ways that we can perhaps avoid this in the future. So a few little musings at the end. So I'm Steve Mackay, the Dean. This is me here. Really what we do as engineering colleges, we have a very practical, focused program of studies ranging from certificates to diplomas to bachelor and master degrees. And in fact, the most recent is a doctorate that we've added in, a professional doctorate. And often people say, well, it's practical. Does that mean it's rubbish? Well, no, actually practical means we try and have a really strong connection with industry. So at the end of the day, we believe probably the most important thing is to focus on applied research, applied study. So focused on what the job market actually is about in engineering and technology. I won't mention where I went to university, but I was very frustrated with a very theoretical outcome. So we're trying to make it a little bit more practical and job focused. So that's our sort of background. And as Nelson Mandela says, education is the most powerful thing we can use to change the world. So that's really a very important point we'd like to make. The agenda today is obviously just a quick welcome, which we're doing. What is catastrophic failure? Just defining what it is. So just putting out the parameters, giving a few examples. I mean, you in your own lives have probably had some examples of failure, engineering failures. Hopefully you haven't been hurt. And then some suggestions of what to do about it. And I've got a few of my own theories, so I'm going to put those in as well. And again, trying to make it as practical and as objective as possible. And then finally, just a conclusion. So it'll probably take about 35-40 minutes, and then we obviously have questions, and hopefully you guys can interrupt me while I'm talking. So if you have any questions or comments, or even better, if you disagree with anything I say, please shout, because that makes it more interesting for everyone else rather than just hearing the same old stuff. So,
sorry, Steve.
Yep,
just to quickly jump in there, yeah, just on the interactive part of it, just to let you guys know, the microphone is disabled for this session, but please feel free to use the chat box if you would like to contribute during the webinar. Thank you.
Yeah, thanks, Riley. I guess we've learned over the last 10 years that the microphone is probably the most important part of the interaction. The problem is that you can hear the clatter of keyboards in the background, or the dog yowling, or the cat shouting, or whatever. So that's why we disabled it. So the chatting in the box, you can all chat there. In fact, I like that hand finger there. Just you see at the bottom, just near the bottom there, you'll see a little chat area. Looks like a little bubble, as my wife calls it. Just type in there if you can all hear us. If you can all just put a little hello, yes, I can hear you, I understand. Just put a little thing in there. Be really good. Just chat in there. It'll be confirming if we're all on the same page. Thank you very much. That's brilliant. Thanks so much. And I also want you, while you're listening to me, to think about a catastrophic failure in your life. A catastrophic failure in your life. It doesn't have to be like the sky fell on my head, or the building exploded, or a car exploded, or something like that. It could be anything, trivial. But I want you to think about a catastrophic failure, and then I want, at the halfway through, near the end, I want you to tell us about your experience with catastrophic failure and how you dealt with it. That would be really, really good. So we'll look for examples at the end. Thank you very much. So catastrophic failure is really a sudden, overwhelming collapse of a system. So basically, you have a crash, you can't unwind it. It's happened. It's over. Recovery is impossible. So once you have a car crash, you can't suddenly just put the car back together again. When a ball hits the ground, it compresses, it bounces back again. It's restored, basically. This is catastrophic failure. Is once you go down this route, it's all over. In fact, it's a concept called entropy, which the engineers amongst us will probably remember. Entropy in the universe is increasing or getting more and more negative. So basically, everything in the universe is winding down. And this, when you have a catastrophic failure, the entropy of the system, the disorder, the chaos of the system is increasing. It's getting worse. So entropy is like a clock, measures how the universe is. And in fact, you'll find the universe is winding down like a big alarm clock. Eventually, it stops. The stars go out, everything ends. So that's the ultimate with entropy. And it's the same thing with a small system, an aircraft or a plane or a car. When you have entropy, it increases when you have a catastrophic failure, and basically you go into a state of increasing disorder or chaos. Cascade system failure means that one system will then fail, leads to another system failing, and it's just going all the way down. So you just have this constant sort of level of failure. Often used for structural failure, in other words, a building. You've got a building, and of course, it collapses, and everything in the building is damaged, and you have a collapse, a lot of bricks, and you can't sort of go back again to what it was. Sometimes you have engineering failures, and I'm sure some of you can think of those, where you have a failure and you bounce back. I mean, you can think of a off the west coast of Australia, there has been a cyclone. It's damaged a town. Certainly, the town's been damaged, but you'll often find that there are power coming into the town, and it's got what we call a circuit breaker, and you may have a fault or something like that. Basically, the circuit breaker trips, the power stops, hopefully, and then you sort out the problem, and then you close the circuit breaker and the power resumes again. So although you have a failure of the power, you restore things and you start again. So that's not really catastrophic failure. So when you have a power failure, you put the lights back on again and you go back to normal. With catastrophic failure, it's over. So there's a few examples of catastrophic failure here, which I'm going to briefly talk about. Tay Rail Bridge, very historical. South Fork Dam collapses as you expect. The unsinkable Titanic, which you all know about. Hindenburg explosion is another interesting one. A big Zeppelin, as we call them, a big balloon full of hydrogen gas, went across the Atlantic. The de Havilland Comet is another really interesting one. Basically destroyed the British aerospace industry and allowed guys like Boeing to take over. Chernobyl, which we all know about, nuclear, and the Columbia Space Shuttle, which was particularly sad, what happened there, and it was probably unnecessary, but most of these are unnecessary, I guess. So Tay Rail Bridge is a very old picture. You can see over here, there's a rather interesting bridge over this sort of lake, or loch as we call it in Gaelic, and you can see it's been basically damaged. So big disaster, and of course center half mile of bridge, which is probably about a kilometer, was destroyed, and of course inevitably destroyed when the train was crossing in a storm. And basically it was quite simply bad design. And we'll come back to the design errors, and again this is a structural bad design, and the replacement was a separate structure. Sometimes you just have to resign yourself to damage and say, well, it's happened, nothing we can do about it. I mean, there's off the coast of Western Australia where the cyclone hit this week, a place called Kalbarri was hit, and they had a wonderful old pier or going out to sea, and of course that's been damaged by the cyclone. Now you may say, well, that's a bad thing, but basically the whole town wasn't designed to withstand a cyclone. So the design wasn't put in place for a cyclone. So, you know, that's something you just have to take on board as far as your structural design. Should you contemplate that level, would the landowners be prepared to pay for that amount of extra cost to make it withstand a cyclone? And obviously the authorities decided that wasn't going to happen. Of course, now you've got to fix the problem. Obviously, if the cyclone keeps coming down the coast and destroying that town, there's obviously going to be a change to the regulations. Okay, there's a few questions going on there. Riley, I think everyone's on board. They're all happy. Any issues?
Yeah, I think we're all good. I think Anile has asked a couple of people if they've got some questions, but I'm sure they'll keep coming through.
And Anile, maybe you can just say hi to us all at this point. Are you on the microphone?
Hello, Steve.
Good to have
Hi,
you here.
everyone.
Thank you very much. Thank you very much for joining in. And Anile is in our Midrand in Africa, Southern Africa, and she's just started work about an hour and a half ago, I think. Anile?
Hello, everyone. I am Anele, the course advisor in the South African office, and I am glad to be with you today. If you've got any questions,
Thank you very much, Anile.
Feel free to ask.
Thank you so much, Anile. I really appreciate it, and obviously good to have you here. If you have any questions, just text it in the box, and we'll chat about it or catch up after the presentation. These presentations, by the way, we've made a consistent effort to do the presentations every week or so, and Riley, Mr. Riley Lesky, is going to be managing them, and I have got our finest academics and me. We are presenting these. I've got about 50 or 60 topics I put through which I want to present, from conveyors to obviously this topic today, and we hope to really contribute to the knowledge in industry with these really useful topics. And there's a lot of academics which are considerably more experienced and knowledgeable than me that will also be presenting. The South Fork Dam in 1889 was another one, and as you would understand that in 1889 the structural standards in those days were completely different to what we have today. So, you know, I don't think this is going to happen today, but even so, there's been a very nasty case, I don't know if anyone can text me, where in today, like this year, there's been a disaster with a dam that collapsed. Can anyone tell me where that dam was? I'm just thinking about it now. Just text it in the box. There was a recent dam collapse, and it was something which was completely probably unthought of. It would never have been thought of 50 years ago that a dam like that could collapse. Where was the recent dam collapse? Just text it in the box, guys. Brazil, yeah, Brazil, there was been a dam collapse. There was been a recent dam collapse in, I think it's Nepal. Does anyone remember that? Yeah, no one. Okay, Brazil, India. Yeah, India. Thank you very much, Krista. Yeah, India, Brazil, Nepal. There was a very bad dam collapse, and in fact, can anyone tell me what caused the dam to collapse? And you know, 100 years ago, no one would have ever anticipated something like that. What caused that dam to collapse? Riley? What did you say?
Natural disaster, maybe.
Yeah, it's actually, the claim is that it's actually due to climate change, which of course 50 years ago you would probably never have designed a dam to handle. As I remember, with the recent collapse, they would never have considered that 100 years ago. And yeah, glacier. Thank you very much, Mule. Exactly, glacier. A glacier above the dam, further upstream, actually broke off, and I think a lot of rocks and stuff like that came down into the dam, and of course penetrated the dam. Now, when the guys are designing the dam 50 years ago, they probably would never have anticipated those. So catastrophic failure actually really means that you not only need to think about today's conditions, but what you anticipate is going to happen in the future, which is probably something which most engineers would never think about. Hey, climate change, a glacier collapsing, damaging my dam. I mean, what on earth are you talking about? So there's a lot of challenges today with our structures. So this South Fork Dam broke really just due to bad engineering. Less than well engineered. There were some repairs done to the old dam. It raised the lake level, which meant, of course, that the pressure on the dam, so this is your water here, the pressure on the dam was excessive, and of course that caused a breach. So that's always a big issue with dam construction, is obviously let the water out, and you obviously, the dam was designed for a certain level of water. They never anticipated unprecedented rainfall, dam broke, and 2,000 people were killed. And of course, there was also a change to the legislation, a result to liability. You can't escape the fault. The unsinkable Titanic has been spoken about many, many times, and I suppose with the climate change today, you probably find a lot more glaciers and icebergs breaking up. There's apparently a lot more floating around. So the Titanic is another typical example, which I'm sure everyone's heard about. In fact, they've got a passenger list of people that died and didn't die, and you can use machine learning to identify, who was more likely to die. And inevitably, the poorer passengers were probably more likely to die on that. It was unsinkable, and basically you had compartments. The ship was broken up into compartments. In other words, areas where there was sealed off, and that meant that 4 out of the 16 compartments had to be broken, flooded with water before the Titanic would go down when it hit the iceberg. And of course, what happened was the ship hit the iceberg, and of course it shook the ship up to such an extent that the hull actually had fracturing on it, and of course that meant that all the compartments were actually leaking, and there was actually separation of the hull plates as well. So that basically meant that the Titanic went down. So it wasn't designed to hit an iceberg. They reckon that it would be resistant because of the compartments all being independent, but of course that didn't come to pass. Hindenburg explosion is another really interesting one. I read the book about this some years ago, and actually this is called a Zeppelin, and it's full of hydrogen. And of course, airships had a bit of a resurgence about 10 years ago in Australia in particular, because they're a very neat way of moving around. You don't have the dynamic problems that an aeroplane has. The problem is that they're just very hard to deal with the weather. This Hindenburg also had compartments in it with the gas, and again, it was designed so that you wouldn't have it would be able to resist some explosion. The problem is that the Hindenburg came across the Atlantic from Germany and went right across the Atlantic, which is quite a feat if you think about it. This airship driven by a small little propeller. And of course, when it hooked up to the tower in the airfield outside New York, hooked up to the tower, there was discharge of static electricity, because obviously this is a different voltage to the actual airship, and of course that discharge of static electricity caused a fire, and which of course exploded. So it was pretty disastrous. German passenger airship. So when it was docking, connecting to a mooring mast, which is a way to hook it up, and pretty bad airship accident, and basically ignition of leaking hydrogen. Now, whether you could have avoided that is debatable with hydrogen. Today they use helium, which of course is inert, less likelihood of an explosion with helium, of course, because it's inert. The de Havilland Comet was another airship, and of course when you get on a plane you're always a little bit twitchy, as we all know, although not many people have been flying at the moment the last 12 months. And the de Havilland Comet was probably Britain's, the UK's launch after the Second World War into jet engine air travel, and of course using this for rapid travel between Europe and elsewhere, North America and Africa, Asia. Unfortunately, what happened was, of course, there were some structural problems with the aircraft. Of course, no one could work out what the problem was. First commercial jet airliner, and in fact, it could have made a huge difference if they had looked at the structural problems before they launched it. It would have made Britain perhaps more of a leader in jet aviation. As it's turned out, of course, America with Boeing, McDonnell Douglas have ended up as being the leaders. Very clean design. 4 de Havilland Ghost turbojet engines buried into the wings, so they're built into the wings. Low pressure noise, pressurized cabin, and this, of course, was the killer punch, a pressurized cabin. And basically you have the aircraft and it's jet, and unfortunately the aircraft is actually pressurized. So you've got a pressurized aircraft, so it's pretty state-of-the-art because it makes it more comfortable for the passengers. And the aircraft is flying, and unfortunately what happened was there's flexing of the aircraft structure, and the windows and the doorways are square, and of course square means lots of stresses at the corners, and these stresses were translated into cracks, and of course that meant that the aircraft then cracked along, and of course that let air in because this is a pressurized cabin, or air out, and of course the aircraft basically with the cracks then just basically exploded. So initially no one knew what the problem was. They thought that there was sabotage, fire, and that's why you've got to be so careful with any catastrophic failure. Before you are sure about the facts, don't be sure about what the problem is until you've actually got all the facts in hand, because you may find it's something different. And in fact what they had to do, because they still, when they had this 3rd or 4th crash, they still didn't know what the problem was. No one could understand, even looking at the wreckage, they couldn't work out what the problem was, and eventually they had to test the aircraft out, stress it in a water tank in England, and after stressing it, they then detected, after many weeks of stress testing, they eventually figured out that there was cracks appearing, and of course it was exploding in the air. So no one anticipated that. Thought, in fact, one of the first things that they thought, besides sabotage, was the actual jet engines were the ones that had caused the problem, and of course it wasn't, just the flexing. Chernobyl nuclear plant explosion is something which obviously all fills us with great, and that is this is the what we call the actual nuclear plant, and the reactor core. They were doing a test of the safety systems, And believe me, I've done tests of safety systems on a to check the work, and often I'm horrified to find out that they don't work. So it's always important to test that your systems that are supposed to protect your plant actually do work. Never assume. And in fact, on the one job I had, we had a bunch of very large storage tanks for fuel, which were pumped offshore for a mine I was working on. And of course, the idea was that the fuel would be stored, diesel, stored, and then in these tanks. And of course, you had liquid foam, which you pumped in, which actually then covered the surface. And of course, then if there was a fire, you'd put it out. So the idea was you had liquid foam, and liquid foam was basically a lot of protein from animals. Pretty disgusting, I suppose. But anyway, that's how you put the fire out. You didn't use water to put out a fuel fire. But of course, what we found was when we tested the safety systems, we found that the safety systems were full with fuel. In fact, they ended up with petrol from another tank leaked into the tank. So in other words, we ended up with the use of the safety systems using petrol to put out a fire, which obviously is impossible. And of course, the safety system had been compromised. So never assume a safety system works until you've tested it. And this is exactly what the Russians did a test of the safety system. And of course, the reactor core ruptured. There where the plutonium is. And of course, you had a core fire and lots of radioactive contaminants into the air. And of course, the radiation was all over Europe. It was the wind blowing across Europe, and of course that excess cancer deaths, probably up to 60,000 people, maybe more. And obviously, huge number of people that didn't die had severely compromised health systems. And that's why you've probably seen the news the last week about Fukushima. Can anyone tell me what's happened with Fukushima in the last week? What announcement have they made there? The Fukushima plant in Japan, they've just made an announcement. Riley, maybe you remember it?
No, I'm not aware of it, Steve, but maybe
Okay.
someone else knows. We'll wait
Anyone
for someone.
else knows here? Yes, thank you, Andreas. Thank you very much. Yes. They want to release the contaminated water into the ocean. So the public perception of engineering and protection isn't very high, unfortunately. The public's not always very trusting. And the Fukushima crew have said, look, guys, we've had an explosion. We've had a lot of bad things happen with our nuclear plant in Japan, but believe me, all will be well. We've just got about, I think, 1 million tons of contaminated water, and we're just going to gradually release this into the ocean. It's all okay, guys. Believe me, it's all okay. Well, yeah, as Mr. Lloyd says there, the contaminated storage tanks are getting full. So we're going to release it into the ocean. No one will notice, guys. Well, very hard in today's very litigious and very cynical environment to make an announcement like that. People don't believe you. You know, you really got to have very strong objective facts. So the Japanese are on a little bit of a problem there as to what they do. And it's a natural reaction. You know, people have seen these huge disasters worldwide for so many years that they're very cynical. They don't trust the powers that be. And that's why nuclear power, for example, if you mention the word nuclear power in Australia or New Zealand, you get a violent reaction. No, I don't care. We are not having nuclear plants here. So, you know, it's a very tricky area to go into. And it's basically because of all these disasters in the past. People don't trust you. The Space Shuttle Columbia is the last one which I really want to mention, and that is a very good bunch of people, and in fact, a woman here, Sally Ride, I think she was a science teacher, actually a science primary school teacher or high school teacher. And I mean, such an amazing crew. They were going to do studies in space, so it's all just brilliant, all highly talented people. And there was an astronaut many years ago who said, would you trust any shuttle that's been built based on a tendering system where the lowest tender wins? Well, you know, even the astronauts are sometimes a bit cynical about some of the results. So this blew up. Destruction after liftoff, death of 7 crew members, and basically an O-ring seal, which is a very modest little seal, basically impinged upon one of the 2 after-booster attached struts. So you had catastrophic structural failure. So particularly unpleasant outcome. So again, this was done by one of the subcontractors to the project, and of course they hadn't considered everything that was going to happen. So that's a few examples of catastrophic failure. I just want to ask if you could text in the box to the right any examples of catastrophic failure you can think of. If you can just text in the box anything you can think of, anyone, anything. It doesn't have to be anything massive, anything that you can think of. Basically something which is an engineering failure which you can't go back on. And as I said, it can be something very minor, something domestic. Any suggestions? Just text in the box on the right there. Failure of tailing dams? Yeah, that's Andreas has got a very good one. And where's the worst example of a failure of a tailings dam? Can anyone tell me which country? Thanks, Andreas, for coming to the party there with a good suggestion. So tailings dam is basically, for those of you not in the mining industry, is basically sludge which is sort of stored, it's very liquidy, it's stored in a sort of dam area, and it's basically as a result of the mining operation. It's very silt-like, very thin mud-like stuff, and it's put into a dam area, and then around the dam you have sort of walls to try and protect it from any breaches. So you have that, and of course you have this tailing, the sludge-like stuff here, and it's often got low-level minerals in it, iron ore, something like that. And there was a very famous one. Okay, Pedro. Yeah, there was a very famous one also in OK Teddy in Papua New Guinea that also breached. The one in Brazil breached, and it's basically the structural failure of the walls, and of course it flooded the villages downstream inevitably, and it's a poorer, weaker part of the community, and they were killed. And you had the sludge pouring down everyone, children, mothers, fathers, killed because of a breach in the wall. And of course, the one in Brazil was owned by 2 very large multinationals, BHP, Australian BHP, and the Brazilian iron ore company. So particularly bad. Yeah, thank you very much. We've got some good examples there. Tsunami, yep, catastrophic failure with tsunami. We had a tsunami particularly bad in Thailand and Southeast Asia. Again, could you have anticipated that? A massive flood, a massive wall of water coming out of the ocean. Very hard to anticipate that. Transformer failure, very good one. Thank you, Cyril. Transformer failure where you have a transformer which has got oil, often used for cooling, and of course the cooling doesn't work, or there's a problem there, or the protection for the overheating doesn't work, and of course you have a explosion of the transformer. You have gas and then you have an explosion, so particularly bad. Bridges are particularly bad. There's a prediction that particularly, for example, countries like America, with a huge investment in infrastructure, there's a lot of challenges there with infrastructure, particularly bridges. And recently there's been a bridge failure in Florida, where the bridge collapsed and also caused deaths. Volcanic eruption, yep, in St. Vincent in the Caribbean. Volcanic eruption, yep, that's a big issue. You can't obviously fly in that. There was a Boeing 747 that flew near Mount Fuji in the 60s, I think it was. They got the dust from the volcanic eruption coming in, and that caused the plane to crash. So there was catastrophic failure there. So that can be particularly bad. And obviously, Pedro said, is the COVID-19 outbreak in Wuhan. That has been a catastrophic failure. That is huge impact on the whole world. I hadn't thought about that. That's a very good one, Pedro. Thank you very much. Penstock failure in a hydropower station, Durban. Thank you very much. Yes, that's right. That Pasamon, Florida International University pedestrian bridge collapse. That's the one in Florida. Yep, that's the one I was thinking of. Irish, thank you. Failure of safety scaffolds. Yep. Scaffolds you have around a building, and of course you may put too much weight, or they're not designed to support the load, or they're just poorly constructed, or they should have been condemned a long time ago. That could cause collapse and people to fall off and die. Building failure all the time, and obviously probably the most famous building failure in recent times has been the catastrophic failure of the World Trade Tower. That was particularly bad. Whether you could expect the designers to design for an aircraft with burning fuel causing a structural collapse is definitely a good question. I believe there has been a redesign to the building codes. Deepwater Horizon, thank you very much. Brilliant. Yep, thanks, Victor. Nixon, Earth Dam failure in Kenya, lives lost. Yep, again, similar to a Slimes Wall Dam, tailings dam collapse. Failure residential, failure of tower crane. Yes, Richard, there's often cases where the tower crane overcorrects. It can't support the load, and then it's collapsed. That's true, that's happened. Lift failures. Yeah, lift failures is actually a particularly interesting one, and a particularly nasty one. I was in a mine in southern Africa called Vaal Reefs. I think it's Vaal Reefs. And the mines go down about a mile, about 1.5 kilometers. And they have a thing called a cage which transports people down into the mine. And a locomotive was on one of the levels, and it actually gone through the barriers and fallen on top of this cage, fell down the shaft on top of the cage, and of course the cage crashed into the 500 meters down, and of course everyone was killed. So again, failure of the protection from this locomotive going into the actual into the shaft, so particularly bad. Yeah, then recently there's been a failure explosion in an engine refinery in Durban. That's true. BP offshore explosion. Failure on Maureen's got a very interesting one. Failure of SRSs in cars. Safety. Maureen, I think you're referring to safety bags, perhaps SRS. I think that's what you're referring to. Boiler explosions are another constant problem. Boiler explosions where a boiler is pressurized well beyond its rating, or there's been some corrosion in the boiler. It hasn't been detected, and of course the high temperatures and the high pressures the boiler is subjected to causes a explosion. And again, the results are catastrophic. So those are quite good. Thank you very much for those suggestions. Really appreciate that. And we've had a brief discussion of causes and fixes. So thanks very much. So obviously some suggestions what to do about this. Well, before we look at what to do about it, let's look at some of the causes of engineering disasters. And I guess we've already summarized quite a few of them. Obviously, the first one is human factors. often the idea is that you have pilot error in a plane, for example, and there's a joke, actually, probably not such a good joke, but it's a funny joke, which is what is the future occupants of a plane when you're flying a plane? What does the pilot have? You have a pilot and a dog in the front. If the pilot in an automated plane in the future, if the pilot tries to touch anything, the dog bites his hand. So to make sure he doesn't touch anything, because the plane is so automated, you don't need any humans flying them. Well, that may be something in the future. The idea is human factors are something which we try and get out of the system, but they're always part of us. And whether you look at driving a car or flying a plane, human factors are pretty critical. Design flaws. Design flaws are a really tricky one, as I've mentioned. And the reason why I say that is, I mean, the dam we spoke about that collapsed in India or Nepal, would the designers have ever anticipated climate change, that a glacier would collapse? I mean, it's very hard for anyone to expect that. Materials failure is a constant problem, and that is the dam structure, the walls, that's a failure, but perhaps the design was that you expected the materials to handle something far beyond what they were designed for. Extreme conditions or environments, and then obviously combination of these. So these are the most often that you'd expect. So they've done some research and on the causes of enduring disasters, and this is probably the outcome. 36% are due to insufficient knowledge, and as I said, that's really hard to anticipate in the future that climate change would cause a problem, or there'll be some extra stresses on your structure that you never anticipated before. Underestimation of influence. So basically, people may never have, when they built a dam wall, never thought that the rainfall would suddenly be so fast, so quick, that it would cause the dam to be under huge extra stress. Carelessness, oddly enough, is only a small amount, 14%. Forgetfulness, error, basically neglect, 13%. Relying upon others without sufficient control, 9%. Objectively unknown situations, basically you don't just really have no information about something. Definition of responsibilities, very small. So basically it's when you're doing the design of a project, construction, you haven't defined for responsibilities. So that's quite small actually. Choice of bad quality, again, very small. So it's really insufficient knowledge of what could impact on the structure. So when the people are doing the design, they didn't realize that there could be a glacier collapse in the future, and if it was built 40 years ago, you wouldn't have thought about that. There's also another catastrophe in New Zealand, which was also mentioned there. Again, that has to do with gas in the underground environment. I was going to talk about that, but unfortunately we're running out of time. We should always strive for, so based on these issues here, we should always strive for a zero accident environment. That's critical. So in some mining environments, in some countries around the world, you say, well, there's going to be a certain number of deaths per year. Well, that's unacceptable. The idea today is zero accidents. We want, if there's a possibility of a death, you say, don't do it. And probably one of the most biggest examples of that from an engineering point of view is the issue of live working. I don't know if you guys know about that, but basically when you have power coming into a building or a factory or a plant, the old approach was to say, look, as long as the guy's safe, as long as he or she, the electrician's working on a rubber mat and is isolated from the power, they can continue to work on that. because it's very important to keep production going. So even with that rule, trying to protect, there were still accidents. So now the rule simply, if there's a hint of a problem, if you're going to be working on power, you switch it off. That's it. There's no ifs and buts. Whereas 30 years ago, you'd say, well, we're trying to work around this to keep the power going. So 0 accidents. That is always important, no matter what the situation. So production is not a good reason to put anyone in an unsafe position. So just a few other little points I just want to mention here. There's a few other little points which will probably come back to me when it comes to looking at the safety issues. And the first one is the law of unexpected consequences. I'm not sure if anyone here knows about the law of unexpected consequences, but basically, when you're doing a design, when you're building something, think about the change that you're making to an environment and the potential for something which you never ever anticipated happening. And probably the best example of the law of unexpected consequences, I always quote, and please forgive me if you heard me say this before, everyone, and Riley. You may remember that with traffic lights today, you used to have an incandescent bulb, a bulb that was burning, and red, green, yellow, orange. That's all been replaced by LEDs. And why has it been replaced by LEDs? Because they last longer. In fact, some wag, when we bought a house recently, said, well, your house will be destroyed, shut down, knocked down long before the LEDs in the house fail. LEDs last forever. So with traffic lights, they've put in LEDs. And in Portland, Oregon, they replaced all the traffic lights at the intersections with LEDs. What happened was the number of accidents went through the roof. So you have a four-way stop. You have traffic lights here and there. And of course, you have a lot of accidents. Why would accidents go up when you replace which I think is a good idea, replace the traffic lights with LEDs? Because they last longer, they're brighter, they're there forever. You don't have any failures. You have unlikely a failure. Why would the number of traffic accidents go up? Any suggestions? Just pop it in the box below there. Uninformed change. Yeah, that's true. Yeah, why are you making the change to LEDs? You obviously probably have a bit of an interruption there, but the traffic accidents went up when they replaced it with LEDs. Line of sight. Yeah, no, that's true. LEDs are that's a very good point, Louis. Thank you very much. LEDs are obviously very focused, so that could have been an issue. You know, they're light. So when you've got an LED here, the angle at which you can see it is obviously perhaps a lot more focused, not as wide, but let's just say there are lots of LEDs. They do have lots of LEDs, so they do have a wide angle of illuminance. Increase of white light. Yeah, that's true. Yeah. It's to do with illumination. Yes, too bright. Well, it's a very strange problem, actually, and I'm sure it would be very hard. And in fact, someone told me about it. Some American told me about it. What was happening, actually, with the LEDs is that in winter, and the LED is so efficient, it doesn't radiate heat anymore. The old incandescent lights used to radiate heat. So in winter, the traffic lights used to be covered up with snow, but the old incandescent lights used to be hot. So they used to burn away the snow, melt the snow, so that the motorists could see it. The new LEDs don't heat up the snow, so often you can't see the light properly. And as someone said there, to do with illumination, Andreas is absolutely right. So basically, you couldn't see the LEDs in the middle of winter because snow was covering them. So people then assumed that they could drive through, and of course they had an accident. So LEDs is a great engineering design, but in fact, had some unexpected consequences. And that's true with any design you do. Anything you do to change, to modify the environment, you will have unexpected consequences. So always try and think what those are. I mean, when the guys are designing this, no one in his right mind would have thought that this could be an issue. So, you know, you just think snow not melting, causing, I mean, what on earth are you talking about? So that is an issue. The KISS principle is another really important thing, which I think is something which we must have in any engineering design. And what's the KISS principle, please? Can you please tell me? Riley, what's the KISS principle?
Wish I knew, Steve.
Riley, well, the time this presentation is finished, you're going to be teaching me lots of things. So the KISS principle is a very important engineering principle which drives all engineers. Anyone engineering professional knows the KISS principle, and it's nothing to do with kissing. It is keep it simple, stupid. So when you're doing a design, thank you, Thompson. Thank you very, yeah, thanks, Edward. Thank you very much, guys. Edward and Thompson had it. Keep it simple, stupid. So when you're designing something and you're designing a SCADA screen for a process plant, don't make the operator's life difficult by having strange little routines and things. Make it idiot-proof so an absolute moron knows what to click and what not to click on the screen. So the KISS principle says, because you can't expect people to jump into your sometimes warped mind and work out what's going on. So that's a very important principle. Engineering should always be simple and stupid. And if it's not simple, it's probably not worth it. It's worth reconsidering. So keep it simple. That also avoids accidents and problems. And the other little one which I always talk about, if there's any doubt, there is no doubt, and that I've stolen from Robert De Niro. When you're designing something or you're putting together, commissioning something, if you've got any doubt about what you're doing, don't do it. In other words, if there's any doubt about an outcome, you know for sure there's going to be a problem. So if you're giving instructions to someone working on a site, you know, please, you need to put on hard hats because you're going into a dangerous area and you're wondering whether that's been done or not. You know for sure that half the people will not be wearing hard hats, so immediately go in and find out what's going on and deal with it. So if you've got any doubt about testing, if you're testing the voltage on a circuit, and as James Teo in our office is saying, when you're testing and you've got some doubts about your multimeter as to whether it's safe or not, always check that it's working. So if you've got any doubt, there's no doubt there's a problem with this multimeter. It's going to read 0 volts when there's actually 3,000 volts on the circuit. So the trick then is to make some way of checking that the multimeter works by checking on a low voltage circuit, and then, oh, okay, it's reading correctly. Okay, I can check high voltage. So always make sure, if you've got any doubt about something, check thoroughly, because you'll always find there's a problem. That's a very important thing. If there's any doubt, there's no doubt. And Newton's third law, I always like to quote. I actually think Newton's third law is probably more important than the first 2 laws. I know everyone thinks I'm probably crazy. And Newton's third law says, Poka Yoke, Maureen says, idiot-proof on Japanese. Yeah, idiot-proof. Thank you very much, Maureen. Absolutely right. Thank you very much. So Newton's third law, and I'm running out of time. Sorry, guys. I meant to keep this shorter. Newton's third law means that if there's any action, there's an equal and opposite reaction. And by that I mean, Newton's third law means that if you're doing anything, any impact on the environment or impact in your organization, you're making a change, there will always be some knockback or kickback or action back to what you're doing. So you always be aware of that Newton's third law in any design you're doing. There's always an equal and opposite reaction. So if you're redesigning something, there's always going to be some impact from your redesign. If you are restructuring your organization, your engineering team, and you're trying to make it better, there'll always be some resistance or impact from what you're doing. So always bear that in mind. We're running out of time, so I'll quickly go through these. So the conclusion is risk management is critical. That means look at the risks, try and assess what they are, And obviously, to come back to our COVID discussion, how many organizations put COVID-19 in their risk register? Not many, I would imagine. Lateral thinking, always try and think of things that could happen on the side. Lateral thinking means try and think of issues which you wouldn't have anticipated. Anticipate the totally unexpected. Get a team of people together to look at things which could happen, which you never would have expected. You know, climate change. Reassess original assumptions. Always check your original assumptions. Are they all correct? Cross-check. Multiple teams solving the one problem. Always important. Fail-safe means that if it fails into the safe mode always. And that's particularly important in electrical. When you design anything electrical on a plant, when the power goes, it shuts down. So always assume the worst. And yeah, as Robert De Niro says, any doubt, there's no doubt. Always like quoting him. Okay, so any final comments here? I'll just pass it back to Riley. Thank you very much. I'm sorry I've overshot the time here. I didn't mean to go on so long. I meant to cut it shorter, but you know, obviously it's always good to chat to you guys. Thank you so much for everyone's involvement. Thanks to Dimitrios. That's very, very kind of you. Thank you very much. Over to you, Riley. Sorry to...
No, you're fine, Steve. No, this is perfect timing. Yeah, no, I think everyone really appreciated that session. Yeah, and we're quite on time, I think. So yeah, thanks, Steve. That was really insightful. And yeah, I think everyone thought how much wide range of knowledge you have of all areas of engineering, and that you could apply them to real world examples as well. So yeah, I think that was really interesting and kept it really nice. So yeah, as mentioned earlier, my colleague Anile will now provide the link to the form for everyone to fill out to receive a digital certificate of attendance for this technical topic webinar in the chat box to the right. It's also displayed on the screen there. You'll receive the certificate within the next 2 days, the 2 business days, as well as the PowerPoint slides as a PDF and the link to the recording of this session. And just to let you know as well, we're aiming to have 2 technical topic webinars a month. So be sure to look out for any upcoming webinars in the future. Our next scheduled technical topic webinar is enhancing energy efficiency via building design, which is being presented by Dr. Anna, our civil and structural engineering lecturer here at EIT. The details are displayed there on the slides, and you'll also be able to find it on our events page on our website. Yeah, so if anyone's interested in civil and structural engineering, that would definitely be a good one to attend. And now I guess if anyone has any further questions for me or Steve, I guess, yeah, please put them in the chat box, and yeah, we'll try and respond over the next couple of minutes.
Thanks so much, Riley. Thanks, Anele, very much for your support. And thank you so much, everyone here, for your incredible interaction. I was quite over the moon. Just very, very good that you guys all did. Aerospace engineering is a very good one. We've got one of our mechanical guys, Melinda. Riley will give him a suggestion to put something aerospace engineering. Very good idea. Thank you very much for putting something together. It's one of our subjects we run, actually. Thanks.
This is our contact details as well here. So that's our website, the address of our head office, our phone number, and as well my email is there at the bottom. If you want to send me an email after this session, feel free to do so. But no, thanks everyone for joining today.
Thanks so much, everyone.
It's been a great session.
Thank you so much, guys. see you tomorrow. Cheers. Thanks, Riley. Thanks.
Thanks, Steve.
Yeah.
Really appreciate it.
Thanks so much. Cheers. Thank you very much, Riley, and safe trip home. Cheers.
Thank you. Cheers.
Cheers.